Hi all, in this video I'm going to talk about earthquake action or earthquake loading on buildings and structures and how we can calculate this action. First, let's have a look at different loadings and how they are applied on for example, three-story building that you can see in this picture. For example, for vertical or gravity loadings, such as impulse and permanent actions, we have uniformly distributed load on unit area. So as you can see, we apply the loading as a uniformly distributed load acting downward because it is gravity loading. For lateral loading, such as wind action, depending on the direction of the wind, the load applies on the area that we have and it is exposed to the wind. For example, the more wall or the area we have, the more wind load we get. It doesn't matter what material your building is made of or anything else. It doesn't really matter how, for example, how heavy is your material. The only thing matters is the area. So the more area gets more wind load. However, it is different for earthquake action. Earthquake action depends on how much mass or weight you have in your building. For example, if we consider in this case, we have three-story buildings and the earthquake acts at center of the mass for each story. So if we consider that the mass of this level is distributed evenly, so the center of the mass will be the same as center of the geometry and acts in the middle of this rectangular, and the force acts in a direction that you apply the earthquake. So if the earthquake is acting this way, the force is also acting that way. So we have a three-story building here. So we have three concentrated mass that we consider for earthquake actions. So each story gets its force. Let's have a look at earthquake action distribution. Again, for a three-story building, the way that the earthquake action is distributed among the different stories will be in a rectangular way, so that it means that the first level, which is closer to the ground, gets less, and the higher you will go, the higher levels, they will get more earthquake loads or earthquake forces. The reason is, so the load from earthquake will distributed based on the weight multiplied by the distance from that level to the ground. So the more distant that level is, the more earthquake action it gets. However, as you can see, the last level, which is the highest level, gets extra forces or extra force, which is because of whipping effect. So whipping effect, you can do more research and read about it more, but it is the one of the phenomenon in the nature. So if you create a wave, for example, if you're here, you have a rope in your hand and you create a wave, in the last point of that rope, it snaps and it has the higher velocity or higher force at the end. So it is exactly what happens during an earthquake. So the ground moves and creates wave in the building, and the last part will have whipping effect, which applies more force on the last level. This distribution is based on same mass for each level. So if you have less mass, this arrow will not be exactly on this rectangle, triangle. So if you have a less mass in the second level, you will get less force. So it's the reason that we prefer to design the building as light as we can. So for example, we prefer timber buildings over steel and concrete because the material is lighter. So consequently, the earthquake load which applies on that building will be less. So if I want to choose material, so it depends on the construction as well. However, if you have like 100% authority to choose material, wooden or timber structure is the lightest, so it is something that you may consider as a first option. After that, steel structure would be lighter than concrete. So concrete is the heaviest. So when you're designing a building for like earthquake, and if you have concrete building, for sure you will get more earthquake forces in the building, and you need to make sure that your building is carrying or resisting against the earthquake action. In this paper this year, we are focusing on static equivalent method to calculate earthquake loading. So in this method, we just assume that the earthquake applies as a static loading on each level, as I showed you, that distribution. So in this method, we just ignore that the force of the earthquake changes by the time. So it is very common for small structures or buildings or like small offices or few story residential building that we use this technique or method to calculate the earthquake action. However, if you want to design a very important structure or building, you need to consider other methods such as time history analysis, which is out of our scope for this paper, but it is something that you should keep in mind. And so in future, if you heard it, you should just realize, oh, it is a method that is considered for more important or like a special design buildings. So it is, what we are using is the simplest method that we are using for small buildings and structures. Let's get started. We have few steps. If you follow step by step, you will be able to calculate the force for each story of your building. So first, we need to calculate the building period. When we say period, it means how long it takes for your building to do a whole cycle. So it means if I want to draw something here, and so here is your building, and you're applying force, shear force, or the earthquake displacement at the base of your building. So your building, if I want to draw it, it goes this way. And when the earthquake changes its direction, your building will come back to the other direction. And it repeats time to time. So the time, this period T, is the time that takes for your building to go and come back. So it's a full cycle, or the period for your building. That would be the time that it takes to go and come back. So it depends on the material that you are using, and depending on the limit state that you are using, that would be different. For example, for designing the buildings, we use ultimate limit state, and for checking the displacement and deflection, we use serviceability limit state. So for designing the building, you need to use this formula to calculate the period of your building, or T1, which is 1.25 kT times Hn to the power of 0.75. This kT, as you can see, can be 0.075 if you have moment resisting concrete frame. If you have moment resisting steel frame, that would be 0.11. If you have eccentrically braced steel frame, 0.06. For all other frame structures, that would be 0.05. So you have to choose among these four options. And Hn is the height in meter from the base of the structure to the uppermost seismic weight or mass. The second step is to calculate the elastic slide spectra, which is CT. When we say CT, CT means a coefficient, which is a function of period. So it doesn't mean that you multiply C by T. If you multiply it, that would be a mistake. So it is just an identification to tell you that this C, which is a coefficient, depends on the period of your building. Same as here, when we say CHT, it doesn't mean that CH times T. So if you multiply it by the period, that would be a mistake. So it means CH is a function of the period. And if the period of the building changes, the CH will change as well. So it is just an identification, same as N. So as you can see, again, N in this formula depends on T, which is the period of the building, and D, which is the distance from the building to the closest fault. So N here is a function of T and D. So here in this formula, we have 1, 2, 3, and 4 factors that you need to find from the tables or calculate from formulas and put them in this formula to calculate C. So we will go through calculation. For example, for CHT, which is the elastic site spectra, we have this table, which depends on the period of your building, which is in second. So if you have, you calculate your period of the building and it comes to 0.8, and you have your building is situated on a strong rock or rock, so you will have 1.12 for CHT. So as you can see, the other thing that affects CHT is the soil under your building. That it is an information that you will get from a geotechnical report. So if you're designing a building, you will receive a geotechnical report, which has been completed by a geotechnical engineer. They went to the site, they studied the rock and soil of that site, and they report it back to you, and they tell you that the that site is made up of strong rocks or rocks, or it can be shallow soil, deep or soft soil, or very soft soil. So as you can see, depending on what soil you have, you will use that column. And also you have to have your period of the structure, and you can choose. As you can see, we don't have 0.82 here. So if your period is 0.82, for example, you need to interpolate between these two numbers to find the correct CHT for the period of the building that you have. The other factor that you need to find is the hazard factor, or Z, that depends on the location of your site. So if you're building a building in Oakland, this hazard factor is 0.13. However, if you're building in Tipuque, this is 0.22. As you can see, it's a very higher than that. Or Rotorua is even higher. These factors depend on how close they are to the fault, and how often earthquake happens, and different factors affect that. But it is something that the engineers have done before based on hazard analysis, and they just came up with this table for you, so you don't need to be worried about any calculation. Just find the city that you are building your building for. For example, in a project, you have Hamilton, so the the Z will be 0.16. In this table, you can also find D. D is the distance from the site to the nearest fault. So as you can see, most of these cities don't have any like number for D. It means they are very far. It means more than 20 kilometers from the nearest fault. So you don't need to be worried about near fault effect. However, for example, Palmerston North, there is a number given here, which is 8 to 16. It means the nearest fault is estimated between 8 and 16 kilometers. It means the nearest fault is in a close distance, which will affect your design. The next factor is R, which is elastic site spectra. So for elastic site spectra, oh, no, it's not. It's a return period factor. So I have to change this. Oh my God. Okay. So for this R, which is the return period factor, you have a look at this table. So based on this table, it depends on how important your building is. You design your building for example, annual probability of exceedance. For example, if you want to design a dam, you probably need to design it for an earthquake that may happen every 500 years, which has a less annual probability of exceedance, and you will get like 1. However, if you are designing something which is less important, you may go for like an earthquake which happens every 50 years, and the probability of exceedance is 1/50, and the factor will be less than 1, 0.35. So you read it from this table for the R. And then for N, T, and D, which is the near fault factor, you have some tables as well as calculation. So the first thing you need to check is if the annual probability of exceedance that you already chose from the previous step is higher than 1/250. It means less important buildings. So if your building is less important and you're designing it for an earthquake, which may happen every 250 years, you don't need to be worried about this factor. So you just consider N as 1. However, if your building is important and the probability of exceedance is less than 1/250, you need to go through the calculation. However, as you can see, if the distance from your site to the nearest fault is more than 20 kilometers, as I told you, you can read it from the table that we discussed. If the diameter, the distance is more than 20 kilometers, again, this factor is 1. However, if it is less than 20 kilometers, it means that it is located in the near fault area, and you need to consider this NTD, which is a near fault factor, to just consider some amplification. So in these two formula, what you need is Nmax. So you can read Nmax from this table based on the period of your building that you already calculated in the first step. So for example, for a building with 0.82 second period, which is less than 1.5, again, Nmax is 1. So if D is less than 20 kilometers, N is equal to Nmax, which is, in our case, in our example that I said, is 1. So again, this T is it's just an identification to tell you that this Nmax is a function of a period, the period of the building. So you don't need to multiply it by T. It is just an identification. So even if you ignore this completely, that is the same thing. However, if it is between 2 kilometers and 20 kilometers, you will go through this calculation, which is not complicated. You already found Nmax, and you have D, which is the distance from the site or the building from the nearest fault, and you just calculate N. This table, I just put it here to just to be familiar with the major faults requiring near fault factors. So as you can see, we have how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 major faults that when you are building a structure in around these faults, you have to consider the near fault factor more than 1. So if you go through this process, you will get that number as well. So I just put these to tell you about the faults in New Zealand. Now we move from step 2, which was calculating the elastic site spectra, CT, to step 3, calculating horizontal design action coefficient. So for this factor, CDT, we need CT, which we already calculated in step 2. So I put step 2. And we have 2 more factors that we need to consider. So this mu, we have a mu, which is the structural ductility factor, which depends on the material that you're using in your building. And it is usually between 1 and 2. It can be equal as well. I don't expect you to find anything or calculate anything for mu, because it depends on the material. And if there is any question, I'll give you the number. For example, I'll tell you, just consider 1.25 for mu. And then we need to find K mu to use it in this formula. As you can see, it depends on the soil classes. So for soil classes A, B, C, D, you use these 2. For example, if again, it depends on your period as well. If your period is more than 0.7 second, you need to consider K mu equal to mu. If the period is less than 0.7, you calculate K mu from this formula. For soil class E, you need to do separate calculation and consideration, because soil class E is in the very soft soil, and usually we have different effect and behavior of building on this type of soil. For SP, we have two different formulas depending on if you are designing your building, which you are using ultimate limit state, or if you are checking the displacement and the deflection of the members, that you are using serviceability limit state. So if you consider we are considering it for designing our members, for SP, we are considering 1.3 minus 0.3 mu. So this mu was what we explained here. So when you calculate SP and K mu, then you put them here in this formula and calculate CDT. Again, I repeat, C bracket T1 doesn't mean that you have to multiply it. It is just an identification to tell you that C depends on the period of the building. That's it. Otherwise, it is only one number, one factor, which we calculated from this formula. Now, step 4 is to calculate base shear. So it is one of the main thing that we are calculating. So when we are analyzing a building for earthquake action, we need base shear as well as the force which applies on each story. So in this step, we can calculate the base shear using this formula. So we calculated CDT, and we have WT, which is the total weight of the building, which we can calculate using sigma WI, which is the total weight of the building. So WI is the weight of each story. So you just, for example, if you have 3-story building, WT is W1 plus W2 plus W3. Here you can see how to calculate seismic weight, which is this WI for each level. So WI is GI, which is the permanent or dead load in that specific story, plus sigma, which is which you need to add them together. Sigma psi E times QI. QI is your live load or impulse action, and you multiply it by psi E. So for psi E, it depends on the application of that building, like that story. So you have to read through and see if what number you need to choose. For example, 0.6 is the earthquake impulse action combination factor for storage application. So if you have a storage application, you consider 0.6 for that level. For example, we have 3-story building. Our first story, we use it as a storage. Our application is a storage. And for example, the third one is like, let's say, is a roof. So for roof without public access, psi e equals to 0. So for example, in a project that we gave you, because you only have one roof here, so when you are calculating, and if you consider that you don't use your roof for public access, so this psi e in this equation will be 0. It means the only weight that you need to consider for earthquake calculation for your building will be only the permanent or the dead load of the roof. So you ignore the live load. Okay. And step 5 is to calculate the equivalent load on each story. So for example, in the first story, we have F1, which is the force applied at the first story. F2 is the force applied on the second story. And F3 is the force, earthquake force applied on the third story. So here is the formula. This Ft is the force that I told you is extra to other levels, and that was because of whipping effect, which is calculated as 0.08 times V, which is the base shear we calculated in step 4 at the top floor, and 0 elsewhere. So you consider it 0 for the first and second and add it to the last story. For level 1 and 2, you can just calculate 0.92 times V, which is the base shear we calculated in step 4, times WIHI. So WIHI, that would be, for example, for level 1, we have W1H1. For level 2, we have W2H2. And for level 3, we have W3H3. And you have to calculate the total WIHI from I equal to 1 to N, which is the number of your stories. So that would be W1 H1 plus W2 H2 plus W3 H3, which is the same. This part is the same for calculating Fi for first, second, and the third level. So this part is the same. You can even calculate it separately and just put a fixed number here. However, WIHI changes for each story. And here I showed the HI for each level. So for first level, HI is from the base to the first level. And H2 is from the base to the second level. H3 is from the base to the third level. Thank you very much for watching this video. Now you can have a look at the example that I provided on the Moodle site, and let me know if you have any questions. Don't forget to like and subscribe.